Okay, hello everybody. Today we're going to be talking about binary operations on a set. So the definition of a binary operation, and I forgot to underline it, so let me do that. So the definition of a binary operation is it on a set S, is it's a function from the Cartesian product of S with itself to S. So typically we denote such a function by a star. And then if you wanted to know the image of a pair s comma t under this function, you denote it by s star t. So there's some properties of binary operations that we're gonna use a lot in algebra. So binary operation is called associative if for all s, t, and u in s, so three elements of s, we have that s star in parentheses t star u is equal to s star t in parentheses star u. So what this means, so the parentheses mean that you do, remember from PEMDAS, that you do whatever is in the parentheses first. So this means you first do t star u, and then you star that with s. Or you can do, on this side, you do s star t in parentheses, do that first, and then you star it with u. And associativity is requiring that these two give you the exact same element of s back. Great. And then the binary operation is called commutative if for all s and t, doing s star t is the same as doing t star s. So both of these things, so something that confused me when I first learned about this was that both associativity and commutativity have to do with the order of things, but that order, but the sense in which by which we mean order is different. So for associativity, the order means like the order in which we apply the star operation. So first do the stuff in the parentheses and then do the stuff outside the parentheses, whereas commutativity has to do with the order in which we write the elements. And these, and as we'll see later, these are very distinct properties, unrelated to each other. And then the third property is that a binary operation is called unital if there exists an element e in S, such that for all s, little s in big S, we have that e star s is the same as s star e, which is s. So applying e to either side of s using the binary operation does nothing. You just get back the same element you started with. And if an element e satisfies this, then we call that element an identity of star of the binary operation. Okay, so I said that all three of these properties are distinct from each other. And we can see this with this cool Venn diagram, which shows that the top circle are all operations which are associative. The left is all operations which are commutative, and the right is all operations which are unital. And so you can actually fill in every single section of this Venn diagram. And that means that these three operations are totally independent from each other. So being associative cannot tell you whether something, a binary operation being associative cannot tell you whether it's commutative or unital, and same with any permutation of those three words. Here we have matrix multiplication with matrices with entries in the natural numbers. This is just regular addition. Regular multiplication is here. This is composition of functions. This is the average function on Q. This is the distance function on the non-negative integers. And then this is just some random binary operation that I made up using this table. Okay, so now we're going to go in and we're going to talk about each one of these separately, and we'll see why they satisfy these properties that I claim that they do. Okay, so here we have our first two examples. So example number one, for both of these examples, and actually for the rest of my life, n is going to denote the natural numbers, which consists of the positive integers. So 1, 2, 3, etc. And our first example is the binary operation usual multiplication. on n. So this is a map from n cross n to n. For example, 3 comma 19 is going to go to 3 times 19, which is 57. And as you might know, 57 is called a Grothendieck prime. Because one time Grothendieck was giving a lecture, and someone asked for an example, and he was doing something related to primes, and so he said, he tried to think up an example of a prime on the spot, and he said 57. Which just goes to show that you can be the best mathematician ever and still not be able to factor two-digit numbers. So this operation, usual multiplication, is it's associative, commutative, and unital. So remember, this was the center of the Venn diagram. And so associativity and commutativity, you know this from maybe a number theory class, or like a set theory class where you constructed the natural numbers or something like this. Or maybe you just know it from using the natural numbers a lot. The unit here, the identity of this binary operation is 1, because 1 times anything is that thing. Right, okay, so that's our first example. Our second example is usual addition. Again, on the natural numbers, so from the natural numbers cross the natural numbers to the natural numbers. So for example, 2 plus, I should have written, just to make it match. This is 2 plus 89, which is 91. Just to make a match above. Right. So, for example, 2 plus 89 is 91. And 91 is provably the first number that looks prime but isn't. And you can look for a proof of this fact. You can go check out this video of Conway proving this on John Conway proving this on YouTube. And this operation is associative and commutative, but it's not unital because there's no element of n, of this n, that I can add to every other element to get back that same element. Right, another way of saying that is that 0, which is the thing that should be the unit of addition, is not in the natural numbers. Right, so this kind of brings up a good point, which is that I could just throw 0 into this set, and then this would be unital. So you can always do this. If you have a binary operation which is not unital, I can just throw in an element, and I decide that this element is the unit by defining multiplication by this element to just do nothing. Conversely, I can always remove the unit and make it not make the binary operation not unital. So for example, here I could just look at the natural numbers except for 1, and then this would no longer be unital. Great. Okay, so here's our next example of a binary operation. So let t be any set, and then we have this somewhat silly notation of t to the t, which denotes the set of functions from t to t. So on this set of functions from t to t, we can place a binary operation called function composition, which you know from high school or wherever. And so it's a map, as all binary operations are, from t to the t cross t to the t to t to the t. Again, kind of a silly sequence of notations here. And this sends a pair of functions f comma g to f compose g, which is the function that sends little t to f of g of t. It is a source of never-ending source of struggle, I think, in a mathematician's life to keep track of which direction to write the composition. But so remember that f compose g in this order means you first do g, then you do f. Okay, so this is this binary operation composition. It's associative and unital. So famously it's associative, and that's, I think, not that hard to check. And it's unital because the unit is the identity function on t, right? That's the function from t to t, which just sends everything to itself. But it is not commutative whenever the size of t is greater than or equal to 3, for which, if this is true, we can use the following example. So if t is just a set of numbers 1, 2, and 3, and we define, let's define f, the function f, to be this bijection, which just swaps 1 and 2 and leaves 3 fixed, and then g is the function, or the bijection, which sends 1 to 1 but swaps 2 and 3. So these are elements actually of the symmetric group on three numbers, because they're bijections. That doesn't matter for this. So then we can compute, so f compose g, right, that's the binary operation applied to f and g. So f compose g of 1, this is f of g of 1, which is, okay, so let's see, so g of 1 is 1, and then f of 1 is 2, great? But g compose f, so if I do the binary operation in the other order, right, if I write the elements down in the other order, g compose f of 1, let's see, so this is g of f of 1, well, f sends 1 to 2, so this number in here is 2, and then g sends 2 to 3, so g of 2 is 3, and you'll notice that 2 is not the same number as 3, which means that the function f compose g and the function g compose f are not the same, because what does that mean for two functions to be the same? It means that they have the same value on every input. Nice, okay, so that's an example of a binary operation which is associative and unital, but not commutative. Okay, so we have another example from our Venn diagram. And this is an example of a binary operation which is commutative and unital, but not associative. So let's explain what this binary operation is. Here, z sub greater than or equal to 0, this is the set of non-negative integers. And the binary operation that we want to consider is the usual distance function. So we'll denote it by d. So what this is a function from z greater than or equal to 0 cross z greater than or equal to 0 to z greater than or equal to 0. And it's defined by d of a comma b as the absolute value of a minus b. So you'll recognize this as the normal distance function on the real line, but just restricted to the non-negative integers. Okay, so let's talk about why this is commutative. So if I have d of b comma a, well, that's by definition the absolute value of b minus a. And so I can just pull out a negative sign from the b minus a. So this is the absolute value of negative a minus b. But because of the absolute value bars, I can just erase that negative sign, right? The absolute value of negative 1 is just 1, and absolute value is multiplicative. So this gives me absolute value of a minus b, but that, of course, is just by definition the distance from a to b. So it's commutative, right? The order in which I've applied, the order in which I write a and b doesn't matter. Why is it unital? So the identity, or an identity of this binary operation is e equals 0. Right, so visually this makes sense. The distance from any non-negative integer to 0 is just equal to that non-negative integer. But let's see algebraically what's going on. So d of a comma 0, this is the absolute value of a minus 0 by definition. And that's just the absolute value of a, but remember the a is non-negative, right? A is greater than or equal to 0, so that's just equal to a. And amazing. And because it's commutative, this also means that d of 0 comma a is equal to a. Great. But why is it not associative? So here's an example of 3 elements of my set that sort of witness the non-associativity. So if I do d of 1 comma 2 to 3, what is this? So d of 1 comma 2, that's the absolute value of 1 minus 2, which is 1, and the distance between 1 and 3 is the absolute value of 1 minus 3, which is 2. And on the other hand, though, if I write the parentheses in the other order, I have the distance from 1 to d of 2 comma 3. Well, d of 2 comma 3, that's absolute value of 2 minus 3, which is 1, and the distance from 1 to 1 is 0, as this shows. So that's the absolute value of 1 minus 1, which is equal to 0. Okay, great. Okay, here we have the next example of a binary operation. which will fill in another section of the Venn diagram. So this will be an example of a binary operation which is commutative, but is not associative and not unital. Okay, so Q here, the Blackboard bold Q will be the rational numbers, and the function, or the binary operation we're going to consider is the average function. The average of two rational numbers x and y is just x plus y divided by 2, which is again a rational number always. Okay, so why is it commutative? Well, average of x and y is x plus y over 2, and the average of y and x is y plus x over 2. And because addition is commutative in the rational numbers, these two are equal. Excellent, so that was not so bad. Why is it not associative? So here again, let's write down some witnesses to non-associativity. So if I just do 1, 1, and 3, if I do the average of 1 and 1, and I take the average of that with 3, that's average of 1 plus 1 over 2, and 3, which is the average of 1 and 3, which is 2. On the other hand, the average of 1 and the average of 1 and 3 is the average of 1 and 2, because the average of 1 and 3 is 2, and that's 1 plus 2 over 2, which is 3 halves, and obviously 2 is not the same as 3 halves, so we have our counterexample to associativity. And why is it not unital? This one's a little more fun. So let's suppose there existed an identity for the average function in rational numbers. So that's an element E, which satisfies the following. For all y in Q, the average of E and y must be y. Before we do any of the algebra, just think about for a second, what does it mean for the average of two things to be one of those things? It must mean that actually E is equal to y. Or you sort of picture, right, the average is like halfway between, like on the number line, the average of E and y would be halfway between E and y. But if halfway between E and y is y, then E must be equal to y. So let's see algebraically why this is true. So if the average of E and y was y, this would imply that E plus y over 2 is equal to y. Just multiply both sides by 2, and then subtract y. So I get E equals y. But this is true for all y in Q. So I have that E must be in fact equal to every element of Q. And this is not possible because there's more than one element of Q. So for example, this would imply that E is 0 and E is 1, but 1 and 0 are not the same. That's a contradiction, and that means that it's not unital. Great. All right, okay, so here is the next example. I forgot to write. Okay, so the next example is a binary operation which is associative, but not commutative and not unital. Okay, so the set on which we're going to define our binary operation is the set of 2 by 2 matrices with entries in the natural numbers. So these are the 2 by 2 matrices, where xij lives in the natural numbers. And the binary operation is matrix multiplication, which you may know from various other sources. So matrix multiplication is associative, and it is not commutative. And both of these are sort of famous results about matrices, which I will cover in my linear algebra series, which is yet to come out, but will at some point. However, it is not unital, and you might be saying, wait a minute, what about the identity matrix? So here I've cleverly restricted the entries of my matrix to the natural numbers, and remember that the natural numbers does not include 0, and so the identity matrix is not an element of this set. Okay, let's see why it's not unital with the restricted coefficients here, or entries here. So suppose there existed some matrix, so that for all other matrices A, we have E times A equals A times E equals A. So let's just let E equal. Let's just say the entries of E are A, B, C, and D. So in particular, if I just take A to be the matrix of all ones, then I must have E times A is A. So let's just do this matrix product. That gives me A plus B, C plus D, and C plus D. And that must be equal to this matrix. However, this implies, right, I mean, if two matrices are equal, then what that means is all the entries are equal, the corresponding entries are equal, and this implies that A plus B is 1. But of course, that's not possible in natural numbers, right? It's not possible to take two natural numbers and add them up and get 1. That's our contradiction. Okay, great. Okay, our second to last example of binary operation. So this is an example of one which is unital, but not associative and not commutative. And this one was the most difficult one to come up with. So I thought about it for a while. Couldn't come up with a nice one, so I just cheated. And so let me show you how to cheat with this type of example. So I'm just going to let S be the set E of symbols E, A, and B, and we're going to define star, a binary operation on S, using a multiplication table. So this just means, so I write down the elements of S here and here, and then inside this grid, I just write what the product of this and this is. So for example, so here I said, so A star B, how do I figure out what that is? I first do the column first. So I take A, and then I look at where B is, and I do the row. So A star B is B. Oh, so maybe it would be nice to circle it. So that is that. Excellent. So I can just write down any multiplication table I want on any set, and this will define a binary operation, since there's no conditions on being a binary operation. And then you just can just check which of these three properties that this multiplication table satisfies. So in this case, it's unital, and the reason it's unital is that if I just look like what is E star anything, so E star E is E, E star A is B, E star B is B. So this, the fact that this row is exactly equal to that tells me that it's unital in one direction, and then the same with the column. So this column is equal to that column tells me that it's unital in the in the other direction. So why is it not associative? So I just cooked it up so that it's not associative. So B star A, well, what's B star A? So B star A is A, there, and then B star A again is just A. But if I reverse the order, if I do a different ordering of the parentheses, first do B star B, let's see what that is. B star B is A, so this is A star, so B star B star A is A star A, and what's A star A? A star A is B, and A and B are not the same element of the set, so it's not associative, and it's not commutative, right, for the exact same reason. Commutativity would mean that it's symmetric across the diagonal, but it's not, right? I have A here and I have B here, so it's not, and that's exactly what these examples show. So A star B is B, but B star A is A. So it's not commutative either. Okay, everyone, we have our last example to fill in the Venn diagram completely. So, an example of exponentiation as a binary operation on the natural numbers. Right. So this map sends n comma m, so two natural numbers n and m to n to the mth power, which you can write as n wedge m, or you can write it as n to the mth power. So this binary operation is it's none of the things. This was on the completely outside of all three circles of the Venn diagram. So it's not commutative. So here's an example of why it's not commutative. 1 to the second power is 1, but 2 to the first power is 2. Those are not the same number. It's not associative because if I do 2 to the first power and then raise that whole thing to the third power, that's just 2 to the third power, which is 8. But on the other hand, if I do 2 to the 1 to the third power, I get 2 to the 1 to the third power, which is just 2 to the 1, which is 2. And 2 and 8 are not the same number. And finally, it's not unital, so let's do a fun calculation to show it's not unital. So suppose there existed an identity, e, in the natural numbers. That would mean that e to the n, well, e wedge n equals n wedge e equals n. In other words, e to the n is n to the e, which is n. So let's apply this to various n's. Right, this must be true for all n. So first of all, this would mean that e to the 1 is 1, taking n equal 1. But it would also mean that e to the 2 is 2, taking n equals 2. So the first one obviously implies that e is 1. And if I combine this equation and that equation, I get that, right, e is 1, so that would mean that 1 squared is 2, which would mean that 1 is 2, which is false. So we have a contradiction, and that completes all examples of all possible triples of commutative, of whether or not a binary operation is commutative, associative, or unital. Great.